Hello, my name is Eric Heim. I'm the principal investigator on this project called Knowing When You Don't Know, Engineering AI Systems in an Uncertain World. And the big idea here is that in order for the DoD to use AI, specifically machine learning, there has to be this idea of calibrated estimates of uncertainty with the predictions that machine learning models give us. Not only we have to be able to quantify this uncertainty, but able to reason about it and potentially rectify it in our models. So I'm going to use this illustrative example to illustrate what I mean by uncertainty in machine learning predictions and why they're important. So imagine you are an intelligence analyst that is trying to find a particular car from overhead imagery. This is something that machine learning is actually pretty well suited to do. So modern object detectors can conceivably do this task. And potentially what could happen is if the machine learning model or this object detector will say, hey, I think that there's potentially two places where this car could be, either this one on the left highlighted by the right or the red box here, and as well as maybe potentially on the right here and highlighted in the red box. But also typically what comes equipped with these predictions in these models is this quantitative estimate of their confidence or conversely their uncertainty in their predictions. So in this particular example I'm showing, this is suggesting that the model is suggesting that the prediction on the left it's 97% confident, while the one on the right it's 98% confident. And if you're an intelligence analyst and you look at these two predictions with these confidence measures, you may say to yourself, well, both of these predictions are very confident, but the car can only be in one place. What do I do? And this isn't just sort of examples that I cooked up here. This is actually well known within the machine learning community that modern neural networks, such as the ones that could be doing that task we just talked about, are drastically overconfident in their predictions. And what this means is that they'll almost always predict with high confidence, regardless of how likely they are to be correct. What would be more useful is a calibrated estimate of their confidence, or conversely their uncertainty. And so this is ones that roughly indicate how likely the model is to be successful in their inferences. So instead of the confidence predictions we had before, if we had the ones here, what you'll see is potentially the one on the left is actually considerably less confident than the prediction on the right, or the inference here. And what this allows a human to do, say like this, an analyst in this case, allow humans to compare these inferences and then make assessments about which ones that they should eventually take action on. So if the intelligence analyst wanted to say, I'm going to dedicate resources to one of these two things to find this car, the one on the right is probably more likely, and the analyst can do so with more confidence. And this brings us to the mission statement of this project. So in order for the DoD to leverage recent advances in AI, modern machine learning techniques must be able to quantify, reason about, and rectify the uncertainty in their predictions. In this work, we'll benchmark modern techniques that will quantify uncertainty, but we'll also develop techniques to identify causes of uncertainty and efficiently update ML models to reduce their uncertainty in future predictions. So like I said, there's sort of the three. There's the quantify, rectify, and reason about. I'll go over each one of these very, very briefly. So first of all, quantify. What I mean by this is how do we have techniques for quantifying uncertainty in predictions practically perform compared to each other? And if you look at sort of the literature as in this field for in machine learning, you can sort of bin a bunch of the techniques. So for instance, we've listed a couple here, papers that are from the post-training calibration literature, as well as Bayesian neural networks and deep ensembles. What's not well understood is how these methods practically compare to each other. So not just in how well they can calibrate confidences, or how can they quantify uncertainty, but also, what is their constraints on data? How much data do they need to actually get this level of performance? Or, how much added computational expense is incurred by using them? So one of the first tasks we'll be doing in this work is be able to actually benchmark these modern techniques so we can understand the practical trade-offs between using them, so we can then potentially apply them to some of the DoDs and problems with this knowledge of their practical limitations. The second one is detecting cause of uncertainty. So what we're asking here is, how do we detect why a deployed model became uncertain in its prediction? So imagine if you deployed that object detector and then suddenly every prediction it gave was uncertain. Certainly identifying the cause of that uncertainty and then allowing us to iterate on that model to improve it is very important. So first we need to detect that there's the cause of this. And so we're looking at two of the potentially many causes of uncertainty that can cause this performance degradation or this increase in uncertainty over time. One of them is data set shift. Basically what this is that the distribution of data changes from what the model was originally trained on. So you can imagine something along the lines of, well, we trained this model, or the model learned its parameters when it entirely on pictures of the aerial images of the summer. And now suddenly as the seasons change, there's snow on the ground. And so there's something fundamentally different about those two distributions. And so suddenly our model may be very uncertain in all its predictions because the imagery that's being fed is very different. So there's some work that we have with one of our collaborators, Zach Lipton, we want to extend and be able to explicitly detect when this data set shift happens, and we want to extend it to the case where we're able to find the direct cause of this uncertainty. And the other potential cause of this this uncertainty could be the emergence of novel classes. So maybe suddenly you have a new model of car you want to detect, but you don't have any training data for that. But so how do you be able to reason about these novel classes as they emerge? So one of the lines of work we want to do is be able to detect, using something called open world models, the emergence of these new classes as they arise in the deployment environment. And finally, we're going to talk about rectifying these models. So once you're able to quantify and detect the cause of uncertainty in a model, and we identify this as a persistent issue that in the deployment environment, how do we rectify this? So once this uncertainty is detected and quantified, how do we make models more confident in uncertain cases in the future? Now, one option is to just simply take all the offending or the really low confidence cases into the deployment environment and have a human sit there and label them correctly. So if we now have these snowy scenes, we have a bunch of labels associated with them that are given by domain experts, and then we retrain our model. Now, the challenge with that is that labeling all of these instances can be very, very human intensive. So maybe we don't have the resources, or we want to reduce the cost, the human cost, in having people label all of these instances. Or so, for instance, in the object detection case, these analysts' time, it's valuable because they're trying to perform their mission needs. So one of the approaches we're going to investigate for that is active learning, basically choosing the most informative instances to have humans label instead of just all of them. And then the other potential challenge is retraining, validating, and deploying a model can be very time intensive. So if we had to go all the way back, into the model development stage, and then really do this heavyweight audit of the model and have experts toil over the different potential reasons why this could happen, and then go through the process of maturing that model and then deploying it in the environment, can be very time intensive. And so what we want to be able to do is to be able to develop best practice to make that process as quick as possible. And when appropriate, we want to do something called online learning, and that once we get new instances to learn from, just update our model in situ. Now, the situations for that are often very rare because updating a model in situ has its own risks, but we may be able to identify cases where we can safely do that. So I just want to give one more perspective on uncertainty AI systems, and this is from the AI engineering perspective. And you've heard a lot today, obviously, if you've been following some of the other talks about what AI engineering and the SEI and our efforts there. But I want to show sort of what this means in terms of this project. And so when you look at the academic literature, they sort of view machine learning as this pipeline you see before you, where you basically have some data, you pre-process it, your ML model makes some prediction directly to a human, but really in reality, it's a much more complex process. So you may have multiple different modalities, and there may be multiple other different system components that do multiple different things. Now, the good thing about having calibrated estimates of uncertainty is that it can actually inform these other components downstream in the AI system. So if the model, for instance, is very uncertain in all its predictions, the system as a whole can determine that those inferences from the model are now unreliable and have mitigation strategies in place. So this actually implies that uncertainty quantification or calibrated estimates of uncertainty can actually increase the robustness of your ML system or your AI system. And similarly, if we by having these detection rectifying best practices, this allows us to iterate better on these ML components instead of having to go engineering these AI systems by these heroic efforts that potentially have to happen if you don't have these best practices in place. So I just want to really just wrap up here with again the restatement of the mission statement. We have some awesome people within the SEI with a variety of backgrounds that are working for us. So that we have Jay, who's an awesome AI engineer, Carol, who's a user experience expert, and John, who's also a fellow ML researcher. But we also have 2 campus collaborators, both from the machine learning department, but Zach has a appointment in Tepper business as well. So Zach Lipton and RT Singh, and they have a long history in studying these types of problems, and we're really excited to work with them. And finally, I just sort of wanted to put this slide up here for everybody to see. So what could all the people out there viewing this video? How do you work with us? And so this project is just starting. We're legitimately looking for these really killer apps in the DoD. We have some lined up, but we really are interested in hearing what the problems they have. And so if you have some domain expertise in a domain that for which ML can be applied, that's something we're absolutely interested in. If you have mission relevant data that we can use, that's great. Even if you just have a problem that you know that ML, you feel though that machine learning or AI can solve, we're interested in that as well. So we'd love to talk to you. So you can send email to this info link right there. And thank you for your time.